Hi, we're going to talk about falling objects. And to start us out, I just want to pull up the kinematics equations and show them to you with y as the variable instead of x. So when we're working horizontally, x is our variable. But when we're working vertically with vertical motion, y is our variable. So all I did is split the x's and the y's here. So it's the exact same equation. But it's velocity in the y direction, acceleration in the y direction, and then the positions and displacement are all in y. So, talking about falling objects, we have this concept of free fall. And free fall is just when the acceleration is due to gravity. So you, I'm sure, have dropped things in your life, and you know that they fall toward the earth, it's because there is a gravitational force attracting them, and that force applies some acceleration downward toward the surface of the earth. So let's look at this motion diagram, and so remember the points are each the same amount of time apart, but the distance depends on how fast they're moving. And then the green arrows are velocity vectors, and the yellow or orange is the acceleration vector. So something starts from, let's say, the ground with a certain speed. So that's indicated by the magnitude of this velocity vector. And as it goes up, you can see here that the velocity is getting smaller with time. The magnitude is decreasing. And that's because this whole time we have this negative acceleration, or really acceleration in the opposite direction of the motion, but it is for our usual way of representing things as negative. So what happens is we start with a higher velocity, but then over time that acceleration is slowing it down because it's in the opposite direction until we get to the very top, and then it's temporarily, really briefly, the velocity is just zero. And then we switch directions. And so we start with zero, and then it starts speeding up instead. And this time it's because the acceleration and velocity are in the same direction. So the same idea we've already talked about with like the signs of acceleration and velocity. Now we're just thinking about them vertically. And then we can also look at the velocity graph and see what it looks like. So the ball will start out with a positive velocity because it's thrown upward. And then that velocity will decrease, which we see because this is the zero velocity equals 0 meters per second line. So it'll decrease until it gets to 0 and it's briefly at 0. And then it will start to increase, but be negative. And so this whole time, we have the slope of this line, which we learned the slope of a velocity graph is the acceleration. So this is a constant negative acceleration. We know it's constant because this is a straight line. And then it's negative because it points down instead of up. Okay. So that's how the graph matches with this kind of scenario that we're looking at. The main idea here is that when you're dealing with this vertical motion, the acceleration is gonna be negative and it's gonna be constant the whole time. It's gonna be this negative 9.8, which is the free fall acceleration, or the acceleration due to gravity near the surface of the earth. And we're not gonna do this ourselves, but if we wanted to, we could test this. You could, for example, since this is a velocity versus time graph, if you had a way of measuring the velocity of an object, you could measure it at different time points and then plot it, and the slope of your line would be pretty close to this negative 9.8. So if we're dealing with this vertical motion, free fall, falling object, then we can actually make a change or kind of simplify our kinematics equation. So first of all, you'll notice that that first equation isn't here, and that's just because in this situation there is acceleration, and that first equation is for no acceleration. So then all I did was replace the acceleration with negative g. So you'll see that in each spot, negative g times the time interval, or negative 1/2 g times the time interval squared, negative 2g times the displacement. So this part is just, if you want kind of a quick way to do it, you can refer back to it. Now we have some examples we're going to go over. I'll read this one first before hopping to the other screen. A heavy rock is dropped from rest at the top of a cliff, and it falls 100 meters before hitting the ground. How long does the rock take to fall to the ground, and what is its velocity when it hits? Okay. So let's start by drawing. We're gonna draw a cliff, the ground, a person holding a heavy rock. And what did we say? This is 100 meters, 100 meters. Okay, I think, yeah, that's good. Let's write our knowns and unknowns. No. So, we can say that our initial position, since it's at the top of this cliff, is 100 meters. So that's us saying that the origin, this is where y equals 0 at the ground. And then y initial is here at 100 meters. Our initial velocity is 0. It says from rest, meters per second. Let's see. I think then, oh yeah, we know what the final position is. Since I just defined it and then didn't write it for you, 0 meters. And finally, acceleration is negative g, or negative 9.8 meters per second squared. Okay, cool. So now we can look at our equations. So there's acceleration. So obviously we're not going to use the no acceleration equation. So velocity final equals velocity initial plus acceleration times the time interval. Y final equals y initial plus initial velocity times the time interval plus 1/2 acceleration times the time interval squared. And finally, final velocity squared equals initial velocity squared plus 2 acceleration times the displacement. And you'll notice that like the acceleration and velocity here don't have a subscript of y, because we're only dealing with things in one direction. So that way we don't have to write as many things. So let's go through these and see what we know and what we don't know. Oh, I didn't even write our unknowns. I should probably do that first. Let's move the equations down. Unknowns. So we don't know the time interval here, and then we don't know the final velocity. And it looks like it's asking for both of those things. So now let's go through. Okay, so we don't know the final velocity, but we do want it. We know initial, we know acceleration, we don't know the time interval. Okay, we know the final and initial position. We know initial velocity, we don't know the time interval, but we know acceleration. We don't know final velocity. We know initial velocity, acceleration, and we don't, oh no, we do know the displacement. So I think since the order of how they ask the question is how long does it take to fall to the ground and then how fast is it going, I'm going to do it in that order because we can. So And that's going to have a sense. The first thing we're going to find is the time interval. We're going to want to start with the long kinematics equation because time is the only thing we don't know in that equation. So let's see. Y final equals Y initial plus initial velocity times the time interval plus 1/2 acceleration times the time interval squared. Okay, so our final position is 0. That's when it hits the ground. And we start from rest, so our initial velocity is 0. So our equation really simplifies here. 0 equals initial position plus 1/2 acceleration times the time interval squared. So now let's just solve for the time interval. So let's subtract y initial from both sides, giving us negative y initial equals 1/2 acceleration times the time interval squared. And then we'll divide everything by 1/2 the acceleration. So that gives us negative y initial over 1/2 a equals the time interval squared. And then we'll square root both sides. That's what is happening when I make that simple, by the way. So that gives us the square root of negative y initial over 1/2 a equals the time interval. And now, so I did show you the equations where we had acceleration due to gravity subbed in. So you're welcome to work from that point. I just think I don't want to skip too many steps. So anyway, I'm going to pull that part in now and say, okay, negative y initial over 1/2 times negative g. So now my negative signs can cancel out, and now I'll plug in numbers. So the square root of 100 meters divided by 1/2 times 9.8 meters per second squared. And this gives us a time interval of 4.5 seconds. So that's how long it takes this heavy rock to hit the ground. And now that we have that information, we can find the final velocity. Although we could have found it with this equation, but I think since this way we don't have to do any extra, not even taking a square root. We're going to use this equation because now we have the time interval. So the final velocity is the only thing we don't know, and it's already solved for. So v final equals v initial plus acceleration times the time interval, and initial velocity is 0. So all we have here is acceleration times the time interval. Now I'm going to plug in negative g, so negative g delta t. And then we'll plug in our numbers. Negative 9.8 meters per second squared times 4.5 seconds. And this gives us negative 44 meters per second as our velocity, final velocity. And you'll notice that it's negative, which makes sense because it's pointing down. So let's take a look at our situation again. And we will put, okay, this whole time we had an acceleration of g, and our velocity was also pointing down because it was just dropped. That's all. Okay, cool. Next example. So we have a person standing on the edge of a high cliff, and they throw a rock straight up with an initial velocity of 13 meters per second. The rock misses the edge of the cliff as it falls back to earth. Calculate the position and velocity of the rock at 1 second, 2 seconds, 3 seconds after it's thrown, and we're going to ignore air resistance, which is good because we haven't even learned about that. So let's draw another cliff. You will see this is a very common theme with the examples in this lecture. The next one is also a cliff. So here's this person throwing the rock with an initial velocity. And let's see. We'll say this initial position. Well, actually. Okay. So someone's going to throw it up with an initial velocity, but let's imagine that they throw it up like from the cliff edge kind of height, so that we can use that as our y equals 0. So y equals 0 at that initial position. Oh, but we do have an initial velocity. Okay, I think that's all right for now. So let's write our knowns and unknowns. See. Well, I just said our initial position is 0. Our initial velocity is 13.0 meters per second. Acceleration is negative g, or negative 9.8 meters per second squared. I think that's all we know. And then our unknowns are the position and velocity at t equals 1 second, 2 second, and 3 seconds. And that's what we want to find. So in order to do this, I mean, it makes sense, but we're going to need more than one equation because we're solving for more than one thing. But I will write out our equations again. And again, there's acceleration, so we're not going to use the no acceleration. V final equals V initial plus acceleration times the time interval. Y final equals Y initial plus the initial velocity times the time interval. That's 1/2 the acceleration times the time interval squared. And finally, the final velocity squared equals the initial velocity squared plus 2 acceleration times the displacement. So let's take a look at these just quickly to see what we know and we don't know and what we want. So we want the final velocity. We know the initial velocity and the acceleration, and then we just have three different time intervals. So, okay, we can use that one. We want the final position. We know the initial, no initial velocity, and yeah, we do have these time intervals, and again, we have the acceleration. For this last one, we want that final velocity. We know initial, no acceleration, and then we don't know the displacement. So it looks like we probably won't use this equation. But it looks like we can use both of these equations as is. So it doesn't matter which order we solve in because there's only one unknown in each case, so we know everything else. So let's see. At time equals 1 second, I guess we'll just solve for velocity first. V final equals V initial plus acceleration times the time interval. So initial velocity is that 13.0 meters per second, and then minus 9.8 meters per second squared times 1 second. So it's actually just going to be 13 minus 9.8, which is 3.2 meters per second. So that's our velocity. I'll put the subscript 1 for at 1 second. Let's do position below this. Final position equals initial plus initial velocity times the time interval plus 1/2 acceleration times the time interval squared. Our initial position is 0. So we can just plug in 13.0 meters per second times 1.00 seconds minus 1/2 9.8 meters per second squared times 1.00 seconds squared. So this time we end up taking 13 and subtracting half of 9.8 from it, and that gives us 8.1 meters. So that's our height at 1 second. Okay, so now let's look at time as 2 seconds. So velocity, same equation, so I'm just going to go straight to plugging in our numbers. 13.0 meters per second minus 9.8 meters per second squared times 2.00 seconds. And this time, we end up with a negative number of negative 6.6 meters per second. So we'll call this V2 for velocity at 2 seconds. And then the position, and again, the initial position 0, so we'll leave that out. 13.0 meters per second, 2.00 seconds, minus 1/2, 9.8 meters per second squared times 2.00 seconds squared. In this one, we get a position of 6.4 meters. So it's still positive, unlike the velocity. Okay, and then finally, oh, I'm running out of room. Wrote too big. Fine, we'll just go to the next page. Okay. Time is 3.00 seconds. So velocity equals 13.0 meters per second minus 9.8 meters per second squared times 3.00 seconds. So that's going to give us a velocity of negative 16.4 meters per second. So that's velocity at 3 seconds. And then the position, 13.0 meters per second times 3 seconds minus 1/2, 9.8 meters. Oh, sorry. It's, we're just going to use 9.8, but at least when I was a student anyway, the precise thing to use is 9.81. Don't worry about that. We're just going to use 9.8. But I might accidentally add a 1 every once in a while, but that's why. Meters per second squared and 3.00 seconds squared. So this time our position is negative 5.1 meters. So position 3 is negative 5.1 meters. So now I want to go back to our diagram and see if I think we can fit it. I can give us a little bit more room real quick. Move over here. Oh, that didn't work. Just move over there. And I'm gonna erase this for right now, but that's the 0. So we have the ball at its initial position with its initial velocity. And then it's gonna be positive 8.1 meters and a velocity of 3.2 meters per second. So let's say this is y1, v1 is pointing up. And then for position 2, it's going negative 6.6 meters per second. So it's moving down. It's only at 6.4 meters, so it's still above 0. So y2 is something like this. And then v2 is going to be down. And then finally for 3, it was negative 16.4 meters per second, so going pretty fast. And at negative 5.1, so that's going to be below this y equals 0. So maybe somewhere like, I don't know, there-ish. That's our third position, and velocity is pointing down. Okay. So, and the thing to keep in mind of what's happening here is just generally speaking with this vertical motion where we're caring about the acceleration due to gravity, if something has an initial positive velocity, as in it has an initial velocity up, it's going to slow down to 0 at one point and switch direction, because the whole time acceleration is pointing down. It means it's slowing down. And we see that it starts with decent velocity, and then we're at position 1, which is high up, and it still has a positive velocity, but it's much lower than our initial velocity. And then it at a lower position and a negative velocity at that point. And then finally, it's past its initial point, so past the 0 mark, and negative pretty high velocity. Okay, so now last example is pretty much the rock situation, but what if they throw it straight down instead of straight up? So we want to find the velocity of the rock when it's at 5.1 meters below the starting point. And it has been thrown down with an initial speed of 13 meters per second. So we will draw this. Here's our person throwing the rock down with its initial speed. And we will still say this is where y equals 0. So what do we know? We know our initial velocity. I'm going to put this as negative because it's going down, negative 13.0 meters per second. We also know the acceleration is negative g, or negative 9.8 meters per second squared. And then we know what this final position is, where we want to find the velocity. Unknowns, this final velocity, and we don't know the time interval, but we might not need that. So our equations, v final equals v initial plus acceleration times the time interval, y final equals y initial, v initial times the time interval plus 1/2 acceleration times the time interval squared, and v final squared equals v initial squared plus 2 times acceleration times the displacement. Let's look at these. We don't know the final velocity. We know initial and acceleration. We don't know the time interval. That one's not going to work. We know the final and initial position. We know the initial velocity. We don't know the time interval. Know that. We don't know that. And then this one, we don't know the final velocity. We know the initial. We know the acceleration, and we know the displacement. So it looks like this is the equation we want to use. So, and we're just looking for that final velocity. So the only thing we need to do is take the square root of both sides, and I'll do that in just a second. 2a delta y. So we're just going to take the square root of everything. And we get v final equals the square root of the initial squared plus 2 times acceleration times the displacement. Okay, and we can plug things in. So this is negative 13.0 meters per second, whole thing squared, plus 2 times negative 9.8 meters per second squared, times, and remember the displacement is y final minus y initial. So that's negative 5.1 meters minus 0 meters. So negative 5.1. Oops, negative. Okay, so this is times negative 5.1 meters. And we get, oh, also with this square and square root thing, this one is not going to tell us the direction of the velocity. So normally in solving your problems, a lot of times, like if it's negative, it'll come out negative. This time we know it's negative because we know it's going down. But just because we're dealing with a square root, it's not going to come out negative. So 16.4 meters per second, and we can just say down as a way to indicate that it's negative. And would you look at that? That is the same thing we got for, see, it was for position 3, which was negative 5.1 meters, and velocity 3 was negative 16.4 meters per second. So that's interesting. We got the same thing as before. And so the reason this is because in the first example, on the way down, when it gets back to the position of y equals 0, at that point, the velocity is negative 13 meters per second. So that point is equivalent to just starting by throwing it down at that speed. So those are the examples. That's all we've got for today, but now you should be more than ready to work to finish your homework problems and work on the activity after this.